In this video, we're going to have a look at how the principle of mathematical induction process works when we're making proofs about product statements. So here we've got a statement, Pn is the product of 1 plus x times 1 plus x squared and 1 plus x to the power of 4, all the way up to 1 plus x to the power of 2 to the power of n minus 1 is equal to a fraction 1 over x to the power of 2 to the power of n over 1 minus x. And we're trying to prove that that is true for all positive integers n. Let's fix that up. And one other condition that we have on here is that x is not equal to the number 1. We have that condition because if x is equal to number 1, then we do have a problem with the fraction here. Let's get into it. So P1. Because this is an equation, we're not talking about an expression. We're going to look at the left and right hand sides. So when n is equal to 1, we have 1 plus x. Really not the most thrilling sort of statement there. Let's look at the right hand side. So we get 1 minus x to the power of 2 to the power of 1 over 1 minus x. That simplifies to give 1 minus x squared over 1 minus x. And by the difference of two squares, we get 1 minus x times 1 plus x over 1 minus x. That simplifies down to give us 1 plus x. So that means P1 is true. All right, PK. So we're going to let 1 plus x 1 plus x squared all the way up to 1 plus x to the power of 2 to the power of k minus 1 be equal to 1 minus x to the power of 2 to the power of k over 1 minus x. For pk plus 1, it is probably helpful again to write what we want. So we want to show that 1 plus x, 1 plus x squared, all the way up to 2 to the power of k is equal to, we're just going to replace k with k plus 1. All right, in this case, it's probably not entirely essential for us to write that because it is quite simple to spot what's going on, but it at least gives us an idea of, sort of what we're working towards. So let's get into actually proving this. So, 1 plus x squared, all the way up to 1 plus x to the power of 2, power of k minus 1, times 1 plus x to the power of 2 to the power of k. Just one thing that I am noting here, I'm making it really explicit that I'm going up to all those factors in pk and then showing the extra bit from k plus 1. I think that's a good thing to do. All right, anyway, that's equal to, using pk again, we're pretty much using it immediately. We get 1 minus x to the power of 2 to the power of k over 1 minus x times 1 plus x to the power of 2k. Now this one actually, I think it's going to work out really quite nicely for us. What I'm noticing is that in the numerator, and in the term that's sort of sitting by itself, this one over here, it looks like we've actually got a difference of 2 squares in here. So I'm going to use that to my advantage. So that means that we're going to have 1 squared minus x to the power of 2 to the power of k all squared over 1 minus x. Look, it's probably important at this point just to recognize how important it is to make sure that we're using the index laws appropriately here, particularly because we've got indices within indices, and it is something that we just want to make sure that we are doing well. I would be making sure that I'm sort of setting things out with as much room as necessary to make it clear what's going on. So you just be really careful and just be really mindful of the index laws from this point. All right, 1 squared, that's just equal to 1 minus x. Now, if we've got something to a power, I'll write this out. Right, x to the power of a in brackets to the power of b, we're going to multiply a and b to get rid of those brackets. So that means we're going to have x to the power of 2k times 2, all over 1 minus x. That's 2 to the power of 1, by the way. So now because, again, using our index laws, what is it? No. First index law, if you've got the same base, we can add those powers together. So you got 1 minus x to the power of 2 to the power of k plus 1 all over 1 minus x. And again, because I did think about it beforehand, I sort of went, what is it that I want to see? I'm now seeing that quite clearly in front of me. So now we get to our final statement. Since P1 is true and Pk plus 1 is true whenever Pk is true, Pn is true for all positive integers n. So that's the process for products. It's very similar to the process for sums. Just sort of being really mindful, and I think particularly this example, the index laws were particularly important. Let's get into it. As always, if you do want to clarify anything,